Hi, I'm Miss Hearn. If you like this video, please give it a thumbs up. That will help other students to find the video. You can also subscribe to my channel, Miss Hearn Mathematics, for more math videos. We will be talking about functions that model things like population growth or radioactive decay. This model works in many different scenarios. And the formula always looks the same. I like to use the version on the right. It doesn't have function notation, but it just makes more sense to me. And that is A equals, and then it has oops, I'm gonna write it big up here. Hold on, my pen's being wonky. Okay. A equals A sub 0 e to the k t. All right. Now, does anyone remember a formula that we have used that looks very similar to that one? About my folks at home, the interest formula, that's right. Yes, Matthew, good. Continuous compound interest. And yes, is that Ariel? Yes, PERT. So remember that we had A equals PE to the RT, and that was when money was growing continuously, right? So we're talking about populations now, but it works the same exact way. In fact, even though we use a K to represent it, this is still a growth rate. And even though we're using this a little bit odd looking symbol A with a little subscript 0, by the way, that's different from A. That subscript, when there's a subscript on one and not on the other, those are two completely different variables. So this is still going, like the principal was the starting amount, right, of money. This is the starting amount of the population. And then A in the PERT formula, A was the ending amount. That was we've referred to it as the accumulated amount. And it still is. It's how much is left at the end. Okay, so in a way, you've already done this. Only the context has changed. Okay. There is one slight variation, which is that with money, we never have a negative interest rate because your money is growing, ideally, not shrinking. But in the case of populations, populations can shrink. So that would mean they have a negative growth rate. So we are going to see that if K is greater than 0, positive, then you have a growth rate. And if K is less than 0, negative, we're actually going to refer to it as a decay rate. So all of this is summarized right here. And you can see graphs showing on the left exponential growth and on the right exponential decay. But we're not going to be graphing them. Our focus is going to be on solving word problems like this one. So here is an example that I pulled off of my labs from the homework. It says the exponential model A equals 95.2 e to the 0.025 t describes the population A of a country in millions T years after 2003. Use the model to determine the population of the country in the year 2003. Okay, so if T represents the number of years beyond 2003, then what is the value of T in this case? T is the number of years past 2003, but we haven't passed 2003. So how many years have passed? 0. That's right. So this is saying T is equal to 0. So look what happens when you plug 0 into this expression, into this equation. We get A equals 95.2 e to the 0.025 times 0. Of course, that's 95.2 times e to the 0. And what is any number raised to the 0 power equal to? No, good guess, but actually no. By definition, when you raise the 0 power, you get 1. So this is actually, and your calculator knows that, by the way. If you use the e to your power button on your calculator and raise it to the 0 power, you'll see that your calculator says 1. So A is equal to 95.2. So the number of people in 2003 was 95.2 million. But let's think about this. This makes sense because I told you that these population formulas would be of the form A equals A0 e to the kt. And remember what A sub 0 represented? The starting amount. And when is this scenario starting? In 2003. So actually, you don't even have to do the work here. If you recognize that it fits the pattern and that A sub 0 is 95.2, you know that's the starting amount. But if you forget and plug in 0, you'll still get the same thing. Okay? Any questions about that one? All right. So there's that. All right, and I want to now change up the problem a little bit. What if I asked you to find the population in 2004? So what would T be in that case? 1, yeah, 1 year after 2003. You can actually get this by taking 2004 minus 2003, which is 1. So in general, if they give you a year, you have to subtract the starting year from it to get the number of years that have passed. All right, so T equals 1. If we plug that in, we would get A equals 95.2 times E to the 0.025 T. So we're going to plug in 1 there. All right, so everybody, you really should be practicing with your calculators. Those of you at home, if you don't have it out, please go get it out. I'm going to pass out these two. I want you to practice with the TI-30X2S. So you're going to write 95.2. You're gonna hit the times button. You're going to hit the second button, second natural log. And then we're going to put 0.025, close the parenthesis, and equals. And what'd you get this time? About 97.61. How about those of you at home? Did you get something similar? Yes, Rosario did as well. Good job. Okay, so now let's figure out in 2005, what would you plug in to find 2005's population? Oh, by the way, that's in millions. So I should write the units. Okay. So what are we going to plug in to find, plug in for T to find the population in 2005? 2, that's right. Find population in 2005. So T is going to be 2005 minus 2003, which is 2. Okay, so now, need my more space here. We're going to have A equals 95.2 times E to the 0.025 times 2. Okay, so how are we going to plug that in? We're going to put 95.2, and then we're going to hit the times button. We're going to hit second, and then we're going to hit the natural log, because above the natural log is the e to the x function. That puts a parenthesis automatically, which is good because we have an operation we have to do in that exponent. 0.025, hit the times button, and then 2, and then close the parenthesis, and then hit equals. Good question, Matthew. The sub-zero is just a way of distinguishing between the variables. So usually we put a subscript of 0 whenever we're talking about a starting quantity, a starting amount. And you'll see that in other formulas as well. Like if you were to take physics and they were talking about velocity, they'll use V for velocity, and V sub 0 will talk about the beginning velocity. Something like that. We use that little, and it also distinguishes the amount here from the amount on the other side of the equation. Those are two different amounts. One reason it has a sub 0 is because it's the amount at time t equals 0. That's why we use that sub 0 there. Okay, good question. So those of you at home, what did you get when you plugged this into your calculator? Anyone type it into the chat for me? I want to make sure everyone's practicing with their calculators. It's very important. You don't have a lot of time between now and the final. Anyone going to be brave and tell me what they got? Rosario, thank you. You got 100.08. Did anyone else get that? Yes. All right. 100.08. Everybody, does anyone have a question about entering it into your calculator? Okay. All right. So now in the next question, I would like to talk about how much the population from the previous problem changed from 2003 to 2004, and also from 2004 to 2005. So how do you determine by what percentage something has changed? You take the amount it has changed and you divide it by the starting amount. That gives you a decimal, which you convert to a percentage. So when we talk about the percentage by which the population grew, you talk about the amount of change divided by the starting amount. Okay, so if we're talking about, for example, from 2003 to 2004, then to find the amount that the population changed means looking at the population in 2003, which remember was 95.2, and it grew to in 2004, 97.61. So to figure out how much it changed, you would take 97.61, the ending amount, minus the starting amount, 95.2, and divide that by the starting amount, 95.2. So that would be, let's see, what would that be? 97.61 minus 95.2 divided by 95.2. Now, there's actually a very common error that students make when they plug this particular operation into their calculator. So I would like you to confirm that when you plug it in, you get 0.25. I would expect that some of you got instead 96.61. And the reason is because this fraction bar, this division bar, acts as a grouping symbol. So it's implied that this operation on top is happening first. It's like it's in invisible parentheses. So you can either hit 97.61 minus 95.2 equals and do that operation first and then hit divide, or just put it in parentheses. Either way, but make sure you got 0.025. All right. So again, we're going to take the ending amount to get the amount of change, ending minus starting amount. So let's talk about from 2004 to 2005. So we found that in 2005, there was going to be 100.08 million, minus in 2004, it was 97.61 million. And we're dividing that by the starting amount, not in 2003, but I'm referring to in 2004, the starting amount of where the change we're interested in. So in 2004, that would have been 97.61. So let's do that operation and see what we get. Did you also get 0.025? And where did we see that 0.025 before? Yeah, it was in the original equation. Remember, the original equation was A equals 95.2 e to the 0.025 t. This is the rate of change. What this means is that every year that passes, what percent of growth do we see? Well, that's the decimal version. And in percent form, what would that be? Very good. 2.5%. 2.5%. Okay, so from now on, you don't have to take the the ending amount minus the starting amount and divide by the starting amount. If you have this formula and they ask you the percentage by which the population grew, where can you look? Right in the exponent here. So this solves the problem for you. This tells you that if you take 0.025 and convert it to a percentage, which by the way, you just move the decimal 2 places to the right, that you get the growth rate, or I should say the percentage by which the population grows each year. So there's actually a problem in your homework, which is going to ask you exactly that. So let's practice. Oh, before we, yeah, I'm gonna practice first, and I'll come back to that survey. Okay, so here's an example from my labs. It says the exponential models describe the population of the indicated country A in millions T years after 2006. Which country has the greatest growth rate? By what percentage is the population of that country increasing each year? Okay, so where are we looking? What would be the growth rate for country 1, for example? Yes, negative 0.006. I accidentally highlighted the T, but I just wanted to highlight the number. So actually, what's happening to the population of that country? It's decreasing. How about country 2, 0.005, and country 3, 0.013, and country 4, 0.024. So which one has the highest growth rate? Country 4 has the highest population growth rate because the K value, 0.024, is the largest. All right, now by what percentage is the population of that country increasing each year? Very good. You convert that to percent form and you get 2.4%. And you're done. One of the easiest questions in the homework if you know what it's asking you for. Okay, so any questions about that one? It says, which function indicates a growth rate of 3% per year? So I'm going to pause this while I find the QR code and everything. So thank you for your patience. So the most popular option was D at 90%. Very good. And that was correct. So how do we get that? How do I know that it's D? We want to look not for 3, but for 3% in decimal form. And so to get the decimal form of 3, 3 has a decimal on the right side. You have to move it to the left 2 places. So it's 0.03. Another way of saying that is, remember the word percent gives you a clue. Cent, how many cents are in a dollar? 100. Cent always means 100, centennial, whatever. It's always 100. So per cent means per 100. So if you divide 3 by 100, you get 0.03. So we're not looking for 3, we're looking for 0.03, and we're looking for that to be the coefficient of t in the exponent. That's where we see the growth rate. So the answer was D. Any questions about that one? All right, let's continue then. So for many of the application problems that you're going to have to work in this section, you're going to have to find K in the formula. Remember the formula we're using? Let's write it. The more times you say it and write it, the better you'll remember it. A equals A sub 0 e to the kt. It's just like the PERT formula. We're just using A sub 0 instead of P and K instead of R. So many times they will ask you to find the K yourself. And the way that you do that is because you're able to do that because you're given information about the size of the population at time 0 and one other time. So, for example, the population of a particular metro area was 1.56 million in 1995. By 2015, the population grew to 4.26 million. Use the exponential growth model to find, it's supposed to say to find only once, an exponential growth function that models the data. Okay, so in this problem, we have to let T be the number of years since a starting date, a starting year. What's the starting year that's implied here? 1995, that's right. So when they say that the population was 1.56 million in 1995, what information are they giving you? What variable represents the starting population? Is it A sub 0, K, or T? A sub 0 is the starting population. So they're actually telling you here that A sub 0 is equal to what? Yeah, we're just going to use 1.56 and consider the millions to be the units. So 1.56. Okay, but they're also giving you another pair of values, another year and the population in that year. It says in 2015, it had grown to 4.26 million. All right, so if 1995 is the starting year, then what is T equal to in 2015? How do we get that number? We take the ending year, the current year, minus the starting year. So we're going to take 2015 minus 1995 to figure out how many years have passed. So you tell me, how many years have passed? 20. So they're telling us that when T is equal to 20, the population A is equal to what? 4.26. Good. Okay. So we are now going to take the information that we have and create a formula from it. The way you do that is you start by just rewriting the formula, but putting, instead of A sub 0, put the starting population, which we said was 1.56. So we have A equals 1.56 e to the kt. Now, E is not a variable. E is the number approximately 2.71. But K and T are both variables, and we want A to just be a function of time. We want to replace K with whatever it's equal to. And we can figure that out just by using this information here. We put this into this formula, and the only variable that's going to be left is K. So we'll be able to figure out the growth rate. Let's try it. So we're going to say A is equal to 1.56 times e to the k. I'm sorry, not A. We're going to replace A with 4.26. We're going to say 4.26 then must be equal to 1.56 e to the k times 20, because we know that when A is 4.26, T is 20. Okay, so there is an equation now that we have to solve to find K, And what kind of an equation is that? Do you remember what we call that when the variable we're looking for is in the exponent? It's just called an exponential. Very good, Cynthia. And somebody else who I can't see. Let me hold on a second. There we go. And Brian, very good. Okay, so that's an exponential equation. How should I begin to solve that exponential equation? You solved a few of these when you did the interest problems where you had to figure out how many years had passed. So the technique is you first isolate the exponential part, the exponential expression. Yes, we will end up using a natural log. That's right, Brian. But first, we're going to divide both sides by 1.56 to get the exponential expression alone. I am not going to put it in my calculator yet. I'm going to wait a minute and put it all in at once so that I don't have any round off errors. So on the left, I'm just going to leave that as 4.26 over 1.56 for the moment. And that's equal to e to the 20k. And then as Brian said, we can take the natural log of both sides. So the natural log of 4.26 over 1.56 equals the natural log of e to the 20k. Now, why do we do that? Why is it helpful when you have an exponential equation to take the natural log of both sides? Very good, that's right. So that's there's two students are responding, one in class and one online. So the person in class said, because you can bring the power out front using the power rule of logarithms, you can bring the power out front. That gets that variable out of the exponent. You can think of it as the challenge of an exponential equation is that the variable is kind of trapped in that exponent. So by taking the log, we can bring that out front. The person at home said, it gets rid of e. That's another way of looking at it. In this case, and this will happen with all of the exponential equations, since the base is e, it's actually going to disappear. So you can think of it two ways. One, using the natural log, the power rule of logarithms, you can think of bringing the power out front, which leaves the natural log of e, which is equal to 1. Or there was another property of logs that said that when the base of the log is the same as the base of the exponential expression, they cancel each other out. Either way, you end up with the natural log of 4.26 over 1.56 is equal to 20k, just the exponent. And then, of course, we need to get k completely by itself. So we're going to divide both sides by 20. So we have this expression that we have to put into our calculator. K is going to be the natural log of 4.26 over 1.56 divided by 20. So let's practice. Let's see if we can all get the right answer for that value. Everybody practice with your calculators. And for anybody who joined us late, I just want to reiterate before I forget that on your final, the only calculator you're allowed to use is the TI-30X2S, and you really should practice with it before going to the final because the order of operations may be different than the one you've been using. And when I say TI-30X2S, I mean only the TI-30X2S, not the TI-30XA or anything else. You have to look on the calculator and see which one you're using. Okay, so let's see what we get here. Natural log of 4.26 divided by 1.56 close parentheses divided by 20. So this is what I typed into my calculator. Natural log, I hit the natural log button, it automatically puts a parenthesis on my screen. So natural log button. And then I put 4.26 divided by 1.56, close the parentheses, that's important, and then divided by 20 equals. Okay, you should have gotten that K is approximately 0.0502. In fact, I'll take it out one more decimal place. I'm going to round off to the 5th decimal place. They'll tell you in my labs which one to round off to. I would, if you go out one more though, you have to round up to a 3. But yes, you got the right answer. Good. Okay. So remember what our goal was. They wanted us to create an exponential growth function that models the data. So they were asking us to write the function. Well, the function that we just found was A equals 1.56E, and instead of K, then we're going to have 0.05023T. Okay, so if they give you the starting amounts and then the population in another year as well, you can find K for yourself and write your own exponential growth model. All right, the next part of this question, let me shrink this a bit. Hold on one second. Okay, so the next part of this question is, what's the predicted population in 2020? All right, so what's that asking us to do? Very good. I couldn't have explained it better myself. She said they're asking us to take the equation that we just found and plug in T for the year 2020. So we need to figure out what T is, and you do that by taking 2020 minus the starting year, which was 1995. So T is equal to 25 this time. So let's see what A, the population, turns out to be in that year. Okay, so everybody plug into your calculator that value. By the way, would you expect to get a number larger or smaller than 4.26? Larger, because the population's growing, right? 5 more years have passed. So, or 10, no, 5, yeah. So we're going to, what did you get? Let's go to 2 decimal places. 5.4767, which rounds off to 5.48. So the units are millions. So the population would be 5.48 million. Okay, any questions about any part of that problem? Now let's talk about exponential decay. It works exactly the same way as exponential growth, except that K is negative in the formula A equals A sub 0 e to the kt. Remember, if K is less than 0, in other words, if K is negative, then we have a decay problem. That means the population is shrinking. Now, one of the things that we do in science is we talk about the half-life of a radioactive substance. And so you need to know what that means when a half-life is mentioned. So a half-life just means the half-life of the quantity is the amount of time it takes for it to decay down to half the original amount. So if you have, say, 1 ounce of something, it's the amount of time that it takes for it to get down to half an ounce. If you have 2 ounces, it's the amount of time that it gets down to 1 ounce. It's always the same, though. It's consistent. So here's an example where you would use that idea. In my labs, I copied this from my labs from your homework. The half-life of the radioactive element unobtainium-41 is 10 seconds. So it takes 10 seconds, they're saying, for unobtainium-41 to get down to half of whatever amount you started with. So it says if 48 grams of unobtainium-41 are initially present, how many grams are present after 10 seconds? Okay, so at 0 seconds, we started out with 48 grams. So how many grams would there be in 10 seconds if the half-life is 10 seconds? 24. How'd you get that? Right. So all you have to do is take half of 48, right? So that's going to be 24 grams. And then it says, well, then what would it be at 20 seconds, 30 seconds, 40 seconds, and 50 seconds? What do you need to do there? Well, notice that in each case, how much time has passed? What are these intervals of time that they're talking about? Every 10 seconds. So every 10 seconds, it's going to have half as many grams as the previous 10 seconds. So we're going to have half of 24 after 20 seconds. So that's going to be 12 grams. And we're going to have half of 12 after 30 seconds. So that's going to be 6 grams. After 40 seconds, it's half of 6. So that's going to be 3 grams. And after 50 seconds, how many grams are we going to have? What's half of 3? Yeah, 1.5 grams. So that looks like a really scary question, but in fact, they're just making sure you understand the definition of half-life is that half the amount of time it takes for it to lose half of its quantity. So the question was, would the amount be equal to 48 e to the 0.5 t? And you're close, but it's going to be negative 0.5 t. Good. All right, let's look at another problem. An artifact originally had 16 grams of carbon-14 present. The decay model A equals 16e to the negative, let me make this a little bigger. I don't know if you can see that on your screen. Negative 0.000121 t describes the amount of carbon-14 present after t years. Use the model to determine how many grams of carbon-14 will be present in 7,758 years. All right, so what are they asking us to do in this problem? That's right. They've already given us the model. We don't have to find K. We don't have to figure anything out about the equation for ourselves in this problem. They're just asking us to plug in. So this is really just a calculator problem. That's just to see if you can find this number on your calculator. 16e to the negative 0.000121 times 7,758. So once again, I'd like everyone to please give that a shot with your calculator. And I see that Brian got 6.26. Did anyone else get 6.26? Yep, that's what I got as well. Very good. A equals 6.26 grams of carbon-14 present. Okay, and that does seem reasonable. I mean, it's only gone from 16 grams down to 6 grams in almost 8,000 years. But if you look at the decay rate, it's very tiny. In percent form, it would still be 0.0121% per year that it's losing. So a very small amount per year. That's the reason that they're able to use carbon-14 to date objects, is because it hangs around for so long. Okay, how about this one? This one, they're not, I noticed right away when I'm looking at this, one of the things that catches my attention is that they're not giving me the model. So what that tells me is I'm probably going to have to figure out the model. So it says the half-life of lead is 22 years. How long will it take for the sample to decay to 80% of the original amount? Okay, whenever they talk about decay rate, you know that you're going to use a model of the form A equals A sub 0 e to the kt, where k is negative. But how to find k is one of the first things you have to figure out. Well, when they tell you that the half-life of lead is 22 years, what that's telling you is that when t is 22, we're going to have half of our original amount left. So in other words, when t is equal to 22, the ending amount, A, is going to be 1/2 of the starting amount, whatever that starting amount was. Now, one way to think about this, and in my labs, they're probably going to work it a little tiny bit differently, but one way to think about this is it doesn't matter how much you started with, just that the ending amount is half of that. So just to make it easier, let's assume that we started with A0 equals 1. Then that would mean that A would have to equal what after 22 years? 0.5, a half, that's right. So in any time that they tell you the half-life value, you can plug in A sub 0 as the starting amount being 1 and A to be a half, and you can solve for the remaining value of K. Does that make sense? Just assume the starting value is 1, then the ending value would have to be a half, and you can figure out what K is equal to. So in this case, that would be 1/2 equals the starting amount, 1, times e to the k times 22. Or you could put, I heard you say 0.5. 0.5 is fine as well. You can put it as a decimal. It's probably easier on your calculator. So 0.5 equals k e to the 22k would be an equation we can solve to figure out k. And what type of an equation is that? Exponential. And how do we solve an exponential equation? We get the exponential part alone, but that's already done for us this time. Then we just have to take the natural log of both sides. So we have the natural log of 0.5 is equal to the natural log of e to the 22k. But what happens when we take the natural log of e to a power? We're just left with that power. So that means the natural log of 0.5 is equal to 22k. Dividing by 22, then k is equal to the natural log of 0.5 over 22. So let's figure out what k is equal to. K is equal to negative point. Yes, I'm going to take this out a few more decimal places. I'm going to go 0.0315. Again, in my labs, they're going to be more specific and tell you how many decimal places they want. All right, so we just found the formula. By finding K, we found the formula, the rate of decay. So so we know that A is equal to the starting amount times E to the KT. So in this case, we just figured out that the formula fits the pattern A equals A sub 0 e to the negative 0.0315 t. Now we can use that to answer the next part of the question, which is how long does it take for the sample to decay to 80% of the original amount? Okay, so when it says how long, that means we're looking for t. T equals what? So this t is going to stay a variable. So that means we need the other values. So somehow it has to be telling us the starting amount and the ending amount. So let's think about that. The sample, so they don't tell us how much we're starting with. We just say whatever sample it is, it decays to 80% of the original amount. When that happens, when they don't tell you, just assume that the starting amount is 1, just like we did for the half-life. Then what would the ending amount be if we assume that we're starting with 1 gram or 1 unit? How much would 80% of 1 be? 0.8, exactly. So we'll use 0.8 for A, and we'll use 1 for A naught, and we'll solve for T. Okay, so that means that 0.8 equals the 1, just 1 times anything is just itself, so we don't really need that. And now we have another exponential equation to solve. The exponential expression is already by itself. So now we just have to do what? We can't divide. There's no coefficients to divide by. You normally, if there was a coefficient here, I would divide by it, but there isn't. So we'll move on to the next step. What did I do over here on the left? Imitate what I did over here. Use the natural log. That's right. So we're going to take the natural log of 0.8. That's going to be equal to the natural log of e to the negative 0.315 t. So the natural log of 0.8 is equal to, what do we end up with on the right side when we do this? Just the exponent. Very good. Negative 0.0315 t. And now we have to get t by itself. And how do we do that? Divide. Very good. So I'm going to divide by negative 0.0315. So that's what we have to plug into our calculator. T equals the natural log of 0.8 divided by negative 0.0315. So everybody help me out here. What do you get for T? Let's go just to 2 decimal places. Anybody want to venture a guess? 7.08. Thank you. Very good, everybody. Okay. And I should write yours, yes. Okay, so let's review this problem because it took multiple steps. So I want you to see when you have this type of problem, I want you to know what your plan of action is. A lot of times the hardest part is, you know, identifying the type of problem and getting your plan together. So whenever you see that they're giving you the half-life, what they're really doing is giving you the information that you need to find K. Okay, so the half-life gives you the information to find K. And how did we find K? We assume that the starting amount is 1. So therefore, the ending amount for the amount of time that's the half-life is going to be a half. So you plug in the half-life 1.5 into our exponential growth or decay formula and solve for K. Then you use that formula to answer the question. So the first step was to get the formula to get K so that we know the formula here. And then they're always going to ask you a question like, how long will it take for the sample to decay to a certain amount? If they don't tell you the starting amount, sometimes they will. They'll say like, how long would it take 10 grams to decay to 8 grams or something like that? In that case, they give you A and A sub 0. But if they don't, just assume A sub 0 is 1 and use the information that they're giving you, which is usually a percentage, to figure out how much A would be. Plug those 2 values in, and then that's how you find your T. Okay, so this is a very common pattern to problems that you will see. Any questions about any part of this problem? Okay. All right, so that's the end of exponential growth and decay. I hope you found this video helpful. If you did, please give it a thumbs up. That will help other students to find the video. You can also subscribe to my channel, Miss Earn Mathematics, for more math videos.